Hello, welcome everyone to this first special session here. So we have the privilege of having the big room for Isogenies. We have 3 talks on Isogenies this morning. And the first talk will be given by Benjamin Wiesolowski, who will talk on their paper joined with Aurel Page on the endomorphism ring problem versus the one endomorphism problem. So please, Benjamin, go ahead.
Thank you for the introduction. So yeah, I'm going to talk about these 2 computational problems and how they are equivalent. It's based on a joint work with Aurel Page. So I'm going to start slowly, even though we've seen a few isogenies this morning. I'm going to give you all the necessary reminders. So an elliptic curve, I'm sure you've all seen elliptic curves before. They are curves defined by a polynomial equation of this form, y² is x cubed plus x plus b. I'm going to work over a finite field. Here are 2 examples of elliptic curves, even though I drew them over the real numbers instead of a finite field. And an isogeny is simply a map between 2 such curves. It's a map that sends points on the first and 2 points on the second. So think about it as a formula that takes a solution of the first equation and transforms it into a solution of the second equation. So that's an isogeny. And that is naturally a computational problem. If you're given just the 2 curves, can you find such a map between them? Can you find an isogeny? That is the isogeny problem. And it's the problem we care about in isogeny-based cryptography. But often, in isogeny-based cryptography, we want to be a little bit more specific about what it means to find an isogeny. And there are isogenies that are more convenient than others to work with. One of these examples is the L-isogeny path. So an L-isogeny path is simply a special kind of easy-to-work-with isogeny. And the L-isogeny path problem asks, if you're given 2 curves, can you find such a special isogeny between them? And that is often what we mean by the isogeny problem. So we have this computational problem, and isogeny-based cryptography is essentially creating cryptosystems and then proving that their security is equivalent to this L-isogeny path problem, which we believe is hard. We believe it's hard even for quantum computers, so we get post-quantum cryptography. Okay, that's at least, it's the expectation, it's the ideal picture. Reality is not always as nice, and what's happening most often is that this nice L-isogeny path problem only serves as an upper bound of the security of cryptosystems. So if you can break it, if you can solve it, you can break all isogeny-based cryptography. And it does not typically serve as a lower bound. Instead, as lower bounds, you get a bunch of different kinds of computational problems that would depend on the scheme you're working with. So there are some nice examples, like the CGL hash function. It's a hash function whose pre-image resistance is provably as good as L-isogeny path. So in this case, the lower bound and the upper bounds match, and we're happy. It's called a hash function, so you expect it also to be collision resistant, and that's where the trouble begins. You can prove that it's collision resistant if this other problem, called one end, is hard. And there's a gap between one end and L-isogeny path, a visible gap. If you look at the problems, and I'm going to define it in a moment, it really looks like it should be simpler. Possibly. And this is not an isolated situation. One end comes up, for instance, also in the security proof of ski sign. The soundness is relying on the one-end problem. So now what is this one-end problem? It stands for one endomorphism, and I'm going to introduce now what are these endomorphisms, and what is the one-end and the end ring problem. So an endomorphism, it's simply an isogeny from a curve to itself. So you fix an isogeny, you fix an elliptic curve E, you can look at all the isogenies from the curve to itself. These are all the endomorphisms. And if you look at all the endomorphisms of E, they form what we call the endomorphism ring of E, written end of E. And you may ask, what does this ring contain? It's called a ring because it's really a ring in the algebraic sense. If you have 2 endomorphisms, you can add them, you can compose them. That's an addition and a multiplication. And it contains a few simple endomorphisms. The first one you can think of is probably the identity. It sends a point to itself. You have also point doubling or negation. These all correspond to multiplication by an integer. Identity is multiplication by 1, point doubling, multiplication by 2, etc. And this is really a ring embedding, and think of the integers as a subring of the endomorphism ring. But we have more. And we know how much more, because if you just look at the additive structure of this endomorphism ring, it's always a lattice. It's a lattice of dimension either 2 or 4. And when I say a lattice, I really mean in the sense of a Euclidean lattice. You have an origin, you have a basis, your endomorphisms are given by integer linear combinations of these basis elements. And when I say that Z lives in there, it actually lives in there as a sublattice. and everything outside this one-dimensional sublattice, they are fancier endomorphisms, not just scalar multiplication. So we have this dichotomy of cases. The dimension of the endomorphism ring is either 2 or 4. 2 corresponds to the ordinary case, 4 to the supersingular case. And the supersingular case is the case we care the most about in isogeny-based cryptography. And now we have another computational problem. What if I give you an elliptic curve? Can you find this lattice? It's the endomorphism ring problem. Can you find 4 endomorphisms that generate them all? Why do we care about this problem? Because it's known to be equivalent to this Li isogeny path problem that I presented before. This endomorphism ring problem is one of the 2 problems from the title of the talk. The second one is the one endomorphism problem, which, as its name suggests, it's the problem of just finding one endomorphism. I give you a supersingular elliptic curve E. Instead of finding a basis, can you find even a single one? One that's not too trivial, one that's not in this scalar subring. Trivially, one end cannot be harder than end ring. Finding one endomorphism cannot be harder than finding them all. And the main result of this paper is that it's actually equivalent. If you have an algorithm to find one, then you have an algorithm to find them all under probabilistic polynomial time reductions. And I'm going to give you a hint at how to prove this result, but first I want to mention a few applications. Why do we care about end ring and one end being equivalent? And the first application goes back to that slide on the security of cryptosystems. So this upper bound on the security, this Li isogeny path problem, we know it's equivalent to end ring. That's previous work. So it's a question about endomorphisms, and then in our lower bounds, we have another question about endomorphisms, this one end problem. And with the equivalence, we now know that it's also equivalent to the end ring problem. And now we are happy because the lower bound matches the upper bound. And these are the first 2 applications. The collision resistance of TGL is equivalent to the endomorphism ring problem. The soundness of Ski-sign is equivalent to the endomorphism ring problem. There's a second application, which is a little bit more foundational. It's a new equivalence between computational problems, between the endomorphism ring problem and the isogeny problem. So now we know that these 2 are equivalent. So this looks a lot like a problem an equivalence I mentioned earlier. We knew that end ring is equivalent to Li isogeny path, but Li isogeny path, it's a restriction, it's a specialization of isogeny. Now isogeny is the more general problem. So isogeny being a specialization of Li isogeny path, we already knew that isogeny reduces to end ring, composing reductions. The other direction is the new one. And the idea of the proof is quite simple. Since one direction is already known, we don't have to deal with it. And the other direction, we're going to use one end instead of one end ring, because now we know these 2 are equivalent, so we need to prove that one end reduces to isogeny. In other words, if you have an oracle for the isogeny problem, you can solve one end. Let's suppose you have an oracle for the isogeny problem, and you're given an elliptic curve E, and now your job is to find an endomorphism of E, a non-scalar one. What you do is you start from E, you generate a random isogeny out of E. You're doing some kind of random walk, and you end up at some curve F. Now you have an isogeny from E to F. You call your isogeny oracle to find a way back from F to E. And if you compose these, your first random isogeny to F, and then your way back, what you get is an endomorphism of E. And we can prove that whatever the oracle for isogeny is doing, what you're going to get here is, with overwhelming probability, a non-scalar endomorphism, so a solution to end ring. And here we don't even need the generalized Riemann hypothesis like we needed in previous reductions of that kind. So this is a totally unconditional equivalence. Not the equivalence. Only one direction is unconditional, actually. The direction from isogeny to end ring still relies on the generalized Riemann hypothesis. A third application has to do with the hardness of end ring. I hope you're convinced now that end ring is a problem we really care about in isogeny-based cryptography. We really need it to be hard, otherwise everything is broken. But just how hard is it? We can now prove that there is an algorithm for end ring in time, essentially big O of square root of p. And you may be wondering, and I know there are many isogeny experts in the room, but didn't we already know that, right? That's kind of the foundational problem of the field. Of course we knew this complexity. Well, to some extent, yes, but we only knew it under some unproven assumptions. We knew how to reach this complexity, assuming the generalized Riemann hypothesis, and now this theorem is saying you don't even need that. You know for sure that we can reach this complexity. The previous best algorithm that did not rely on an unproven assumption only reached linear complexity in P. P here is the characteristic of the finite field we're working with. The idea of the proof is just an application of the previous application. I mentioned in the previous application that now we have a reduction from end ring to isogeny that is unconditional. No need for the Riemann hypothesis. So now, to solve end ring, we just have to solve isogeny. And what's nice is that for isogeny, there's a very simple algorithm. It's just a meet-in-the-middle algorithm that works in time square root of P, and we are done. So there are a bunch of applications. I hope you're convinced that it's kind of a useful result to know that one end is equivalent to end ring. And now I'm going to give you an idea of the proof, the main ideas and the main obstacles we had to overcome. Here's what we want to do. Of course, one end looks simpler than end ring. So all we need to do is to prove that end ring reduces to one end. Suppose you have an oracle for one end. An oracle, if you feed it an elliptic curve, it's going to spit out an endomorphism. And you're given a curve E, and now your job is to find all of the endomorphisms of E, or a basis of its endomorphism ring. The first idea, in fact, it's not really even an idea, it's idea zero. It's the trivial thing you may think about. You have a curve, you have an oracle to find endomorphisms, and you want to find them all. So you call your oracle on it. You get an endomorphism of your curve. Now you call it again and again and again. It gives you a bunch of endomorphisms, and you hope that at some point you've found enough. So first step is you generate many endomorphisms. Second step is at each new endomorphism, you check whether you're done, and if you're done, you extract a basis from the generating set. The second step, figuring out whether you're done, whether a collection of endomorphisms generates the whole thing, is efficient. It's just linear algebra, more or less. The problematic step is the first one, because what you're doing here is you're just calling an oracle again and again and again on the same input. You have no guarantee that the oracle is even going to give you different distinct outputs. Maybe the oracle is deterministic, so maybe this is just going to give you always the same endomorphism, and you're making no progress by calling your oracle many times. So the first real idea was introduced in this 2018 paper. Try and randomize the oracle. You have an oracle, can you transform it in a way that you make sure that the output is kind of random, so you can hope that calling it multiple times will give you something new? And how do you randomize the oracle? So you have this oracle O, and you're going to build a richer one, which we call rich O. It's a randomized version. It works as follows. This rich O, if you feed it an elliptic curve E, is going to first do a random walk from E to some other curve F. So you just generate a random isogeny. Now F is a random curve. You call your oracle on it, and it gives you an endomorphism of F. What you want in the end is an endomorphism of E. But now you have one. You can just follow the orange path, then the blue path, then backtrack along the orange path, and that's an endomorphism of E. That's the output of rich O. So you've built another oracle that on input E spits out an endomorphism of E, but now it's randomized. So here's the algorithm again, but we replace the original oracle with this richer one, and we hope that now it's random enough. And that's basically the heuristic claim in that 2018 paper. Now with this randomized oracle, everything goes well, we hope. It eventually produces a generating set. The problem is, not only we can't prove it's true, it actually fails. There exist oracles for which this algorithm never terminates. So we need another idea. And the other idea consists in saying, sure, it's not going to terminate. You're never going to get a generating set of the whole thing. But surely at some point it stabilizes. You're going to find a generating set of something, after which point you're never going to find anything new. And we want to understand how does it stabilize. So we prove two theorems. The first is about the behavior of the oracle. The oracle spits out an endomorphism, a random endomorphism, and we want to understand its probability distribution. We prove that the output is, in a sense, stable under conjugation. By that, we essentially mean that any output, any possible output alpha of the endomorphism is as likely as any of its conjugates in the ring. With that, we're hoping that if we eventually stabilize, we're going to stabilize at a generating set of a ring, which is itself stable under conjugation. What are these? That's the second theorem. The subrings of the endomorphism ring that are stable under conjugation are these very special subrings of the form Z plus a scalar multiple of the whole thing. Putting these two together, we know that the algorithm will eventually stabilize at some subring of that form. The good thing is, if we have a generating set for such a subring, we can extract a basis of the endomorphism ring in polynomial time. The bad thing is this eventually here. Eventually means polynomial time. So we are not really happy with that yet. I'm going to tell you in a second how to make that faster, but first I want to highlight this first theorem. This is actually the tough part. It's where all the fancy number theory is hiding. And the way it works here is you have a statement which you want to prove about elliptic curves. And the first thing you do is kind of a standard trick in Isogeny-based cryptography, is to apply the De-Ring correspondence, which translates your question on elliptic curves into a question about quaternions. And we like quaternions. They behave nicely. We know a lot of things about them. Now that you have a question about quaternions, we need a new trick, which is more unusual, I guess, in isogeny-based cryptography. We're going to apply what's called the Jacquet-Langlands correspondence, which is going to transform your question about quaternions into a question about modular forms. Now you have a nice modular form to study, and finally we apply the Leens bound on its coefficients, and this bound will give us precisely what we want about the distribution of the output of the oracle. So I'm not going to say much more about these steps. It would take much more time than I have, but I can tell you at least what we have now. Here's the algorithm we've arrived at. It's essentially the same as the first one, but instead of waiting for a generating set of the whole thing, we wait for a generating set of a subring of that special form z plus m times the endomorphism ring. Once you've reached that form, you recover a basis of the whole thing. As I said, this now terminates, which is much better than the original reduction, which didn't even terminate. But in the worst case, it's going to terminate in exponential time. That actually depends on the oracle. There are good oracles for which this will behave well, but in the worst case, it's going to be exponential time. So we need to do something else, and the last idea is to introduce this lazy reduction here. Whenever the oracle gives you an endomorphism, you're going to do this lazy reduction step. So what does it mean? It's some kind of algebraic reduction you want to apply to the endomorphism to make sure that it's the best it can possibly be. But then you realize that this algebraic reduction is really costly because you're going to need to factor a bunch of large integers, and that's really bad. So instead of an algebraic reduction, you do some kind of lazy version where you try to factor as hard as you can in polynomial time, and you're going to fail, but it's OK. Whenever you fail, you're going to find new factors, and your factorization is going to get either easy in the end or not needed. And with this lazy reduction, we can reach a polynomial time. And the main message here is that you've used a one-end oracle to find the whole endomorphism ring. You've used one end to find them all. Thank you for your attention.
Are there any questions for Benjamin? Yes.
Hi, so thank you for the talk. Since we're working on a finite characteristic, we always have the Frobenius endomorphism. And isn't it like a trivial solution that we can always get for the one endomorphism problem?
It is trivial. It is, in fact, too trivial, because the Frobenius endomorphism, in general, is just going to be multiplication by minus p. So it falls in that forbidden easy subring of just scalar multiplications.
Thanks.
In rare cases, it's going to give you non-trivial information. If your curve happens to be defined over fp instead of fp squared, then you have the fp Frobenius, which is non-trivial. And indeed, that gives you some information. But these curves are extremely rare.
I know you said you didn't really want to talk about it more, but could you still add a few more words to this Jacquet-Langlands correspondence, because it sounds very cool.
Oh, OK. So it's do you know anything about modular forms? So it tells you something about a modular form you can create whenever you're considering quaternions or actually more general arithmetic rings. And from the modular form you get, you can deduce certain of its coefficients, and the bounds on these coefficients will give you bounds on the Hecke operator. Does that speak to you? So when we're doing a random walk in the isogeny graph, you can link that to an operator on the space of on the probability space on your graph. And the random walk you're doing corresponds to an operator on your graph, which is essentially a Hecker operator. And the eigenvalues for the Hecker operator, you can read them out of modular forms. So that's why we transform through this Jacquet-Langlands correspondence into a question of modular forms. Is that helpful?
Cool. Thanks.
If there are no further questions, then let's thank the speaker again. And the next speaker is Eugenio. Okay, so the next speaker is Eugenio Paracucci, who's going to talk about joint work with Guido and Lucian Hanslik. I hope I pronounced this more or less correctly. Who is going to talk about mix and match attacks on Schnorr-type blind signatures with repetition. So please.
Thank you very much for the introduction. My name is Eugenio Paracucci, and I'm a PhD student at CISPA. Today, I will present mix and match attacks on Schnorr-type blind signatures with repetition. As we told, it's a joint work with Guido and Lucian Hanslik. In this talk, we're gonna have a break on isogenies, actually, and delve into blind signatures. I hope you will still enjoy. The main goals of these talks will be to define what Schnorr-type blind signatures actually are and present an attack on that schemes and apply them in particular to isogeny-based blind signatures. But first, let's give some context on blind signatures. Blind signatures are an example of interactive signatures, and they involve two main characters, a user on the left and a signer on the right. The signer with a secret key is able to issue signatures on messages which can be publicly verified using a public key. On the other hand, the user has a message, and after the interaction within the signer, will output a valid signature on that message. We require two main properties of blind signatures. We want the protocol to be blind, in the sense that the signer doesn't learn anything about the message they sign. And also, an unforgeability property, which very informally states that the user needs to interact with the signer in order to get a valid signature. So since this concept will be central in this talk, let's spend more time on it. This notion is called one more unforgeability. And suppose we have a malicious user interacting with the signer. And we require that after one interaction, one execution of the protocol, the user is not able to output two valid signatures on two different messages. More generally, after L interaction with the signer, the user will not be able to output L+1 valid signatures. We require this property to hold for any adversary, any malicious user, and for any positive integer L. This notion comes into two flavors, sequential and concurrent. We talk about sequential security when sessions are opened sequentially. That is, before opening a new session, one must close the previous one. If users are able to execute sessions in parallel, we are in a concurrent setting. And concurrent security is actually stronger than sequential security, but is also more natural and is what one would like to achieve in practice. Okay. Our case of study are Schnorr-type blind signatures, which are an example of three-move blind signatures. And the idea behind these schemes is to leverage the construction of digital signatures based on identification schemes and the Fiat-Shamir transformation. And also add on the user side two functions, blind and unblind, in order to achieve blindness. Let's make this construction more explicit. So the starting points are identification schemes, in which we have a verifier and a prover. The prover wants to convince the verifier of the knowledge of a secret key without revealing any information about it. So first, the prover commits to the secret key, to the verifier. The verifier challenges the prover with something taken from a challenge space, C, and receives back from the prover a response, and eventually outputs yes if the prover succeeds, and no otherwise. We want that an honest prover will always succeed with the verification, with the identification, and a dishonest prover can cheat with the probability at most 1 over cardinality of C. We will also require the honest verifier zero-knowledge property, which states that there exists a simulator that, given on input a challenge, will output a valid transcript of the protocol having that challenge as challenge. If this challenge space is small, then the cheating probability of a dishonest prover will be negligible, non-negligible, and what we usually do is to repeat the protocol n times in parallel to increase security. And now, instead of having numbers, we have vectors. We have vector of commitments, vector of challenge, and vector of responses. And the cheating probability now becomes 1 over cardinality of C to the n, which is negligible in n. We can turn an identification scheme into a digital signature using the well-known Fiat-Shamir transformation. And the idea is to replace the interaction with the verifier with a random oracle. This is the construction. And also in this case, when the challenge space is small, we take parallel repetitions, and numbers becomes vector. We will use the bold notation to denote vectors. OK, with these two ingredients, identification schemes and Fiat-Shamir transformation, let's consider this construction. The signer first sends a commitment to their secret to the user. The user computes a challenge according to the Fiat-Shamir transformation and sends this to the signer, and receives back a response, and output the signature RS on M. If you look at the construction, this will lead to a valid signature according to the Fiat-Shamir transformation. But actually, there is a problem in this scheme, and in fact, this scheme is not blind, because a signer can record the transcript with the user and then link the signature with the user's identity. So what we do is to add functions, blind and unblind, on the user side to achieve blindness. And again, if challenge space is small, perform parallel repetitions. Okay, so this is how a Schnorr-type blind signature looks like. And we are going to see in a moment how to attack these schemes. In more specific, we are going to describe an adversary A against the one more unforgeability of Schnorr-type blind signatures with small base challenge space, and by small we mean polynomial in the security parameter n, and performing n parallel repetitions. We have two attacks. The first one is called n out of n, and the attacker will output n plus 1 valid signatures after executing n concurrent sessions with the signer. The second variant is called 2 out of n, and as in the previous case, the attacker will output n+1 valid signatures after finishing n sessions, with the difference that in this case, the system only allows 2 concurrent sessions at a time. So the difference between the two is the number of concurrent sessions allowed. In both cases, the runtime will be big O of n times cardinality of C. I want to describe you the n out of n attack in an unblind setting, and for simplicity, and with for the special case n equals to 3. So we have a malicious user opening one session with the signer and receives a vector of commitment. Instead of performing the protocol honestly, can do the following. The attacker can do the following. Can first simulate a valid transcript of the Sigma protocol thanks to the honest verifier zero-knowledge property, and replace the first component of the vector of commitments with the D, challenge D. Then we'll find a message M such that the challenge for that message and that commitment starts with the D. And this requires an expectation cardinality of C many queries of the random oracle. So in this case, the attacker already knows a valid response for the challenge D, since by construction it's F, and therefore wins an additional response for any challenge involving R1. So this is the core idea. And with this in mind, so in the real attack, the attacker will open 3 concurrent sessions with the signer and receives the commitments. Let's visualize them in this table. Then, for each session, we'll select one commitment as, for example, the blue diagonal, and mix this commitment together to create the commitment for the forgery. And also compute the challenge for the forgery, the message M star. Then, for each session, we'll generate a valid transcript of the base Sigma protocol. And as we have just seen in the previous slide, now for each session, before we'll replace the left blank squares in the table with the commitment EI. And as before, we'll look for messages MI, such that the challenge, computed according to Fiat-Shamir transformation, has DI as component I. And finally, we'll send these 3 challenges for each session, respectively, to the signer, and receives responses back. With these responses, we'll be actually able to respond to these 4 challenges, and then output 4 valid signatures after 3 concurrent sessions, and then breaking the one more unforgeability of the scheme. I would also talk about generalization of this attack. The core idea that we have just seen is to find a message M such that the challenge starts with a given challenge D. And this requires cardinality of C many queries and n sessions in total to break the one more unforgeability. What we can do instead of brute forcing just one challenge, we can brute force the first S challenges. And this now requires more calls to the random oracle, roughly cardinality of C to the S many calls, but less sessions. And in the end, this will be the runtime. So this little generalization will lead to a trade-off between the number of calls to the function h and the number of sessions required for breaking the one more forgeability. I would like to conclude this talk with some implications of this attack. And as I mentioned briefly at the beginning, concerning to the affected schemes, we have CSI from Katsumata, Lai et al. And this is the first isogeny-based blind signature schemes, which is based on a blinded it's a blinded version of CSI fish, which is in turn based on a Sigma protocol with a bit challenge, so the challenge space is cardinality 2, and perform parallel repetitions. So this will fit in our scenario, and on practice, with this attack, we're able to forge 129 valid signatures after 128 concurrent sessions with the signer. So as to sum up, we have seen basically an impossibility result on Schnorr-type blind signatures. So parallel repetitions of a small challenge space are not concurrent secure. So while parallel repetitions work for Fiat-Shamir transform, they doesn't work for blind signatures. But however, just this is the last thing I want to say, is if one would like to hope to construct a potential secure blind signature scheme, one following this paradigm, one must start with base identification schemes with exponentially big challenge space. So this is all, and thank you very much for the attention. And, yeah.
So thank you very much for your talk. Are there questions from the audience? If not, this morning we saw an identification scheme with an exponentially big challenge space, namely SkiSign. Have you had a look at that? Can that be blinded somehow? And
this is an interesting question, and yeah, this would be the SkiSign has actually exponentially big is a signature scheme following this paradigm and with exponentially big challenge space. So this would actually be a potential candidate, but maybe this wasn't. I cannot go back. Okay.
Oh.
Well. I gave definition of Schnorr-type blind signatures, but this is just a definition, it's not constructive. We don't know, in general, how to blind a Sigma protocol. So if someone has ideas, please come to me, and yeah, I was very happy to talk about.
Are you aware of efforts that have been done for?
Excuse me?
Are you aware of efforts that have been done for?
Are
you aware of efforts that have been done to create blind signatures out of SkiSign?
I heard that there are some people that are also interested, but yeah, it seems hard as far as I.
Okay. Yeah. Thank you. Are there other questions? If not, let's thank the speaker again. So then we move to the. Are you all set, Boris?
Yes.
Yeah. So then we move to the last speaker of this morning's session, who is Boris Fuotsa, who is going to talk about joint work with Luca De Feo and Lorenz Pani on isogeny problems with level structure. So please go ahead.
Can you hear me? Yes? Okay. So I'm Boris, and I'm going to, thanks for the introduction, Wouter. I'm Boris, and I'm going to talk about isogeny problems with level structure, which is a joint work with Luca and Lorenz. So the talk is going to be organized as follows. First, what I mentioned, we will talk about the isogeny problem with torsion point information. Then we will introduce level structures to show a unified view of problems that occur in isogeny-based cryptography. Then we will present a reduction that allows us to have other reductions that are important to have a better general view of the problems that occur in the field. So without any further notice, let's move to the isogeny problem with torsion point information. As Benjamin said this morning, an isogeny is just a map between two elliptic curves that it's like a many-to-one map, okay, that takes many points to the same point. And this many here, you can see it as a degree. So if I have an isogeny from a curve E to a curve E prime, then the degree of this isogeny is just the number of points that are sent to infinity. In this picture, for example, there are 2 points that are sent to infinity. You can see that every point on the right has 2 pre-images on the left, okay? The red point is sent to infinity, but the other point which is sent to infinity is in fact the point at infinity, which I cannot represent on the graph. So in isogeny-based cryptography, there is one starting problem, which is the pure isogeny problem, which can be stated as follows. You are given 2 curves, E and E dash, oh, there is a typo there, E and E dash, with the promise that there exists an isogeny between these 2 curves, and you are asked to find such an isogeny, okay? There is no restriction on the isogeny, no restriction on the degree. You just need to find one isogeny between these curves. As Benjamin mentioned again earlier this morning, he said this is the base problem in the field, but protocols don't usually directly, the security of protocols is not directly based on this problem. This is just an upper bound on the security. So one of the problems that occurs in the field, or that was occurring up to 2 years ago, was the supersingular isogeny problem with torsion point information. So the very first isogeny-based protocol was using group action, isogeny group actions on ordinary curves, but these isogeny group actions are subject to sub-exponential quantum attack. So in 2011, Zhao and Defeo, they asked themselves, can we move away from these group actions and use ordinary, like normal supersingular isogenies? But you have the one problem that occurs is that normal supersingular isogenies, they don't commute in general. So they needed something more to make these isogenies to commute, and what they found was that if you reveal some torsion point images through these isogenies, then you can make them to commute, okay? So this is where the torsion point information comes from. It was introduced to make the supersingular isogenies to commute, and to hence obtain like a Diffie-Hellman type diagram. So what is torsion point? When you look at an elliptic curve, then you look at the n torsion points, which are just the points that when you multiply by n, you get the point at infinity. Then they form like a group, which can be generated by 2 elements, okay? So the n torsion can be generated by a basis PQ, where P is a point of order n, Q is a point of order n, and P and Q are linearly independent. So when we talk of torsion point information, it means revealing the images of such a basis, okay? So when we talk of an isogeny problem with torsion point information, it means you are given the 2 curves, but you are also given the image of a basis. So P prime here is the image of P, and Q prime is the image of Q, okay? But since they form a basis, then you can also look at this like in linear algebra, where when you talk of a map, you look at it as a matrix, okay? So if you fix the basis P prime and Q prime on E prime, then you can see an isogeny which maps P and Q to P prime and Q prime as just a matrix operating on this basis, okay? So in this case, when you reveal the exact torsion point information, then you are just considering the identity matrix, okay? We will later see that you can now consider many other matrices, which gives you problems that are slightly different, but this allows to have a general view on many problems that occur in the field. So now let's look at the history of the supersingular isogeny problem with torsion point information. So the problem was introduced in 2011. In 2016, it was proven that you can, in fact, exploit the torsion point information to design adaptive attacks, and this is why you have the Fujisaki-Okamoto transform. There was a Fujisaki-Okamoto transform in Psych. There were several works that were trying to design a passive attack on XIDH exploiting this torsion point information, but in the results, they required like a big amount of torsion point than what was in fact available in SIDH. So this work did not apply to SIDH, but they were showing that we should look at SIDH with one eye because the torsion points there they may be very harmful to the scheme. But then in summer 2022, you had the very great work of Wouter and of Castryck and the crew, then followed up by Mino, Martindale, Pani, Pope, and Wesolowski, then Robert, who just finished everything. And the main result is the following, is that if you are given two curves with the promise that there exists an isogeny phi of degree d between these two curves, and you are given the action of this isogeny on torsion points of order n, where n squared is greater than d, then this is in fact just giving away the isogeny. So this is a representation of the isogeny. So Robert and all these results, they show how you can in fact evaluate this isogeny on torsion points using this information. Okay? So this is a big picture of the SIDH attacks, and they allow you to have a representation of an isogeny just by providing the images of smooth order torsion points. So with this, we can now move to the isogeny problems with level structure. So recall that in the SIDH setting, I said you are given two curves. You are also given the action of the isogeny on torsion points. And this can be seen just as a matrix if you fix the basis. Okay, it's true that it's only the one who knows the images of the torsion point who see this as a matrix, but when you use this representation, you have a global view of the problem, in fact. So what is a level structure? A level structure is just a basis of the torsion points up to a multiplication by a matrix which lie in a subgroup of the invertible matrices modulo n. Okay? So what happens now if I go into the SIDH problem? I don't reveal the exact torsion point images, but I reveal them up to a matrix which lies in a certain subgroup gamma of matrices that are invertible. Then we obtain what we call the gamma level gamma SIDH, which is just the isogeny problem with torsion point information up to a matrix element which lies in gamma. Okay? And even though this looks weird, level structure are mathematical objects that are well studied in mathematics, but just bringing it this way into the SIDH, we can see that this gives an upper bound on almost every protocol, on the security of almost every protocol in the field. So if we look at what groups corresponds to what protocol in the field, we can see that the SIDH, the plain SIDH scheme corresponds just to multiplying your torsion points by the identity matrix, which means you give the exact torsion point images to your secret isogeny. If we look at M-side, which is a countermeasure that was suggested to the SIDH attack, then it corresponds to multiplying your torsion point images by a diagonal matrix where the entries are equal. Then if you look at orientations that are very well used in isogenies, you can see that it corresponds to multiplying the images of your torsion point by random scalars that are different. Then if you look at SIDH signatures, it corresponds to just given the image of one subgroup, which corresponds to multiplying your torsion points by, there's no pointer. It's only now that I noticed. It corresponds to multiplying your torsion points by a matrix which is of this form. Then you also have what corresponds to giving the exact image of one torsion point. So in what will follow, we will prove that, in fact, the gamma-1 SIDH problem is somehow equivalent to the plain SIDH problem. So having the image of one point, modulo some small conditions, is equivalent to having the images of two torsion points. And this is another main contribution of the paper. So let's then move to this reduction. So the gamma-1 SIDH problem is the following. You are given two curves for which, with the promise that there exists an isogeny, and you are given the image of one torsion point of small order through this secret isogeny. The first thing to notice is that these points, they define two parallel vertical isogenies. Okay, parallel in the sense that there exists another isogeny on the bottom, which is also parallel to the previous one. So what happens if the order of the points is a square? It means you can, in fact, split these your vertical isogenies into two. Then you get another parallel isogeny in the middle. And what happens is that if you flip the upper vertical isogenies, you get now information in two directions. Okay? So before you had information in one direction of order n, but now you have information in two directions, but of order square root of n. So you can already see here that you move from a gamma SIDH problem where you have gamma 1 SIDH problem where you had information on a point of order n to a plain SIDH problem where you have information on points of order square root of n. You can also do the reverse reduction, and this gives an equivalence between the two problems. It's just that you need to note that the order of the point is there is a square root when you move to the plain SIDH problem, and when you move to the other one, then you need to square the order of the points. So the reduction works when n is smooth, of course, because you need to solve some discrete logs when in the reduction. So with this reduction, we can prove several other reductions. So the hard arrows are natural reductions. The dashed arrows are the ones that are proven using the previous reduction that I described. And then there is no pointer. The other arrow between SIDH and lambda lambda is just specific cases. There are reductions in very specific cases, but not in general. So with this, we can now have a very nice picture of the field right now. So this is a very, there are not all the schemes in the field here, but this gives like a nice picture of the security of schemes in the field right now. So as we said, if you have full torsion point information, then your scheme is broken. That is the line, there's no pointer, that is the red line up. So plain SIDH, where you have full torsion point information, okay? Then it is also known with reductions due to Wesolowski and many other authors, Petit, Eisentrager, and al., that if you know the full endomorphism ring, then the isogeny problem is easy and all its variants, okay? So the other red line corresponds to knowing the full endomorphism ring. For group actions means you know the suborder of your endomorphism ring, and this is like halfway in the endomorphism, and this corresponds to C-side, scallop, and every other isogeny-based scheme where you know a suborder of your endomorphism ring. And in this case, you have a sub-exponential quantum attacks. That is why it is in orange. Then, all the countermeasures to SIDH, M-side, FESTA, bin-side, and many more, probably. Here you have gamma SIDH problems, where in M-side, it is the lambda lambda, as we mentioned before. Then in FESTA, you reveal the torsion points up to multiplication by a matrix, where a diagonal matrix, where the entries are different. And then in SIDH signatures, you somehow reveal the image of one subgroup because you are revealing two parallel isogenies, so you somehow reveal the image of the kernel of these two parallel isogenies. So it corresponds to the gamma SIDH, where gamma is the group of matrices of that form. The most interesting part is that ski sign is here at the bottom, so it's sort of the most secure isogeny-based scheme if you want to look at what information is provided, because there is no torsion point information and there is no information about the endomorphism ring of your curve. So if you had to take one message, it is that, to take one message home, is that when you reveal full torsion point information, your scheme is broken. When you reveal the whole endomorphism ring, your scheme is broken. When you use orientations, you have a sub-exponential quantum attack, but you can increase the parameter to have secure protocols. Then there are these between none and full that are secure, as we know today, but maybe future work would help us to better understand these problems. So I think with this, we can stop here and go for lunch. But before lunch, I would like everyone to choose his peel. Red or blue? Red, red. Raise your hands. Red? Okay. I've taken a picture, so those who choose red, you have to eat fondue before you leave Switzerland. Those who choose blue, you have to eat raclette before you leave Switzerland. Then I will stop here. Thank you.
So thanks a lot for the nice talk, Boris. Are there questions from the audience? If not, yeah, so I was wondering, so M-side, is there any progress on, I think if one of the gamma level structure problems could be broken at some point, it
yes,
probably
so thanks for the question, and that's a good question. So yes, so when I present the problems here, it means the generic problem. So in some particular cases where you have some more information, like in the case of M-side, where if you know a small endomorphism of the starting curve, or if the curve is even defined over FP, then your scheme is broken. And thank you for that question. And for Festa as well, if you know a small endomorphism that acts in a very particular way on the basis that you use for your problem, then it may be broken. So yes, so this problem, when I present them here, is just the generic, like, you don't assume the generic problem, but if you go into some specific cases of the problems, it may happen that you have some attacks. Yeah.
Okay.
Thank you for the question.
You. Are there other questions from the audience? Yes?
Hi, thanks for the talk.
Yes.
And also that now, like, the focus was on n torsion with n general number.
No, n smooth, sorry.
Okay, yeah. So, like, when n stopped being smooth, or n is like, maybe smooth, but not a power of 2, or not a power of a small prime or something like that, there are like other like fine-grained distinction between the problem, for example, on trust, like how much we can trust them or not.
So here, for example, so everything relies on the SIDH attacks, and the complexity is O of the smoothness bound of the torsion points. So if n is not smooth enough for you to have polynomial algorithms, then this starting point already fails, which means we don't know how, if you have an isogeny and you have its action on non-smooth torsion point, on torsion points of non-smooth order, it still reveals some information about the isogeny, and it still even uniquely defines the isogeny if the torsion point is, the order of the torsion point is greater than 4 times the degree of the isogeny, but we don't know how to recover the isogeny. So it's still a lot of information regarding the isogeny, but the algorithms we have now don't allow us to solve it. So if you take torsion points of non-smooth order, it's still a lot of information, but we don't know how to exploit it for now.
Thanks.
Yeah.
Thank you for that question. If there are no further questions, then this probably means everybody's hungry for fondue. And what was the blue option again?
Fondue and raclette.
Raclette, okay, yeah.
Depending on some, okay. Yes, fondue and raclette. So it's cheese and bread. You take your bread, you put into the cheese, and you eat it. And raclette, you have your cheese, and you melt it on what you want to eat with, either potatoes or, yeah.
So you'll have cheese for sure. So thanks again, Boris.
You're welcome.